Alrighty, so we got to talk about the project first, and then we'll see if we can get into the new stuff. If not, new stuff can wait till Thursday. Excuse me. So this was our stacks and queues project. Bunch of input we had to deal with. We had to put plain items into a queue, which is pretty straightforward. We had to put the train items into a queue of stacks, right, stacking them 5 high. So that was kind of the tricky piece here. So when we go to solve this, we're going to try and break it down into a few different steps, and we'll see how well that goes for us. So I think, let me start a new project. We'll call this one project 3. Maybe if it'll type for me. Wow. That's weird. All right, I'm gonna just start over there then. New project. All right, that looks better. Project 3. Doing the window. Come on. All right. So when looking at the rubric too, right, we wanted to use classes in this design, and then we need to make sure our calculations are right, and then we use stacks and queues. So thinking of some classes here, right, I think maybe like the first one might just be the doc. And again, it doesn't have to be a class necessarily, but if we have a doc class, we can say, here's all the input, go set all these things up, and then we can get the train items off the doc, we can get the plane items off the doc. Maybe, you know, that's one option here. So I like this idea then, so we would have all of our inputs getting passed to the doc. We need to know how many trains and planes, and really items for each one, essentially here. Now, this first line of input really doesn't actually matter unless we want to validate anything, because the second line of input is all the trains, the third line is all the planes, and then the number of items for trains, number of items for planes. So I'm really just going to ignore the first one, and what I really want then is the number of items for each train, the number of items for each plane, and then the train items and the plane items, essentially. So we'll take the number of items per train, we'll take the number of items per plane, we'll take the train items, and we'll take the plane items. Again, that will probably all fit on one line on yours, but I'm zoomed in a little bit here, so I think that's pretty close. Now, what we need to do when we're done is have the queue of stacks for train items and the queue for the plane items, and then I probably want to have my train set up and my plane set up. Right, so like thinking about those things. So if I need some other values here, I might think, hey, I might need a class for train. So if we think about a class for train, what does a train need to know? Well, it needs to know what its number is, right? Train number. And it probably needs to know the number of items needed, or number of items needed, something like that. Then we can set those things. Train number is the train number, and my self.number of items needed, is the number of items needed, and then I need to know the time it takes to load. So I can have another value here for time until fully loaded, or something. Right, so this way I can store these values places, and I'll assume it's 0 until I know otherwise, right, in train. So train will represent the number that it is, the number of items it needs, and the time until fully loaded, right? So then the doc can set up a list of trains maybe. So I might have a bunch of trains then would equal a list, right, of trains, and I can add a bunch of trains to it, right? So then, I don't know, for value in, and we can take our number of items per train. Now, if this is already a list of integers, really easy. If it's a string, I have to do some splitting. I don't really know exactly how we'll handle that yet, but for now I can probably just assume it's a list of integers. We can fix that later if we need to. Sure, so for each value in the number of items per train, I can take my trains and I can append a train given that value. Or I'm sorry, the train number then will be, I guess I gotta go, I guess if we enumerate this then, right? Enumerate number of items per train, I'll get the index and the value. I'll have the index plus 1 as the train number, and then I'll have the value as the number of items for the train. So one way of setting up trains. And really, plane then is going to be the same thing here. So we'll make a class for plane. It needs the plane number and the number of items needed. Lowercase p there, right? There we go. And now if you see two sets of code with the same things here, and the only things different are some variables, we could be thinking, oh, maybe I don't need different classes for these. Maybe these can all be one class. I like the way you're thinking. That's great. So let's change that then. Let's make this a transport method here. So it has the number, has the number of items needed, and then the other thing that was different is the amount of time it takes. So we'll say like round trip time or one-way time. How about like one-way time? We can add that in. So then we'll have our number is the number. We'll have our number of items needed, the number of items needed. We'll have the time until fully loaded, and our one-way time is the one-way time. So then when I make a train, now that's just a transport method, and the one-way time is this is going to be either times the train number, or this is a one-way time, like multiple. Either way we want to go about it here, right? We could calculate it as the number times 1, or I could just pass it the index number here. Either way is probably going to work for me here. So let's do the one-way time. We'll just say is index plus 1. And that will serve as this value here for trains. And then for planes, we'll make a list, and we'll do the same thing here. But we're going to enumerate our number of items per plane. We'll add a new transport method. Index plus 1 is the value, and this is that number then times 5. Right, because that's the one-way time for planes, right? 5 times the plane number here ought to get me there. And then I can append that to my plane. So I have a list of trains with their expected number and how long it takes to get there, one way. And I guess I can get rid of those spaces. My list of planes. Then I need to make my queue and my stack, right? So I think we can just import those, right? We had Python stack. Wasn't there a stack class? Wow, I don't remember this. In data structures, stack class. I thought it was in like collections, wasn't it? The linked list? No, I just want a stack. Why am I not? Wasn't there one? I know we have the queue, right?
I just made my own private.
Okay. Yeah, we can steal ours, then that's fine. We've written them before.
What do you think for you to use like a list stack or a linked list stack?
So with the list-based stacks, right, we get on average good performance, but eventually you might have to do a resizing. With the linked list, you never have to resize ever. So slightly faster performance-wise to never have to resize with the link-based one. Where we're trading off a little bit more memory usage for it, which is probably fine.
Well, in this case, as we are only building from 0 to 100, right?
Yeah.
Like the maximum size will always be 100.
Yeah. Yeah, so it's easy to use an array because we know it's only going to be 100.
Okay.
Mm-hmm. So what do we have here? We had our circular queue, we have the faster queue, we have the stack. All right, so we can use our stack here. And then we can use we wanted the circular queue, right? Was that the better one, or was it the, oh, the deck. Yeah, we don't need the deck. So I think we just use the circular queue. Sure. And it's probably, I should add in the other letters here, right? Here. And we can say we got it from here. We'll be good, right? I'll put that above for stack and queue. Here's for stack, and here's for queue. Right, just citing our source. We're gonna be good. Okay. So then we need a queue then for our plane items. We'll have our plane items. A circular queue, sure. And then for our plane item in my plane items.
Sir, what are you using the circular queue?
It's just the queue I have that's fast.
Oh,
Yeah, it could be a linked one. I don't think we have. Did we end up writing that one? I don't remember if we did or not.
no, I used from the book.
Yeah, that's fine. Yeah, any queue is fine. This is the one I happen to grab. Yep. So for that item in the queue, we just go and add it to the queue. So our plain items dot. Why don't we have our? It's NQ. Yep, NQ. There we go. NQ, the plain item. Right, and that is the value then. Plain items. Oh, I can't have this in here twice. Shoot, plain items Q. So for plain item, plains item. I wondered, okay, plain items. Gotta make sure I don't use the same variable name twice. We'll do that. And then for the stack, or the queue of stacks, right, this will be my train items queue of stacks equals a circular queue. And now I need to add every item to a stack 5 high. Right, so for, I guess we can use, we got a couple different options here. So if we enumerate, we could say for index and value, or train item, in enumerate, right, our train items. The first thing we need is a empty stack, right? So I'll make a stack first. So here's the current stack. Here's the stack. So if the stack isn't full, I want to add to it. So if the length of my current stack does not equal 5, what is it not like that? Got psi? What? Did I not add that to the stack method class? We didn't add a length. Oops. Okay, so we got to add a length. Find length. And return self.data. The length of self-data. There we go. Make sure we can actually get a length out here. Sorry, I didn't have that one in there before. All right, so now if the length is not 5, I'm going to take my current stack and we're going to push the train item. If it is 5, right, or maybe we do that one first, I guess, right? That's probably even easier. We'll say if it is 5, then we want to queue that stack and make a new stack. So we'll take our train items queue of stacks and we want to enqueue the stack. We can say stack equals a new stack, or the current stack, right? Sorry, current stack. Current stack equals a new stack. Then, regardless of what happens here, we can push that item onto the current stack. It's probably a little cleaner, that way we don't have an else, right? When that's done then, once I've processed every single item, let's add the current stack to the queue. Right, add the last one. So it's not guaranteed to be a multiple of 5. In the example it was, but if you had like 7 items, I'd end up with 2 left in a stack and nothing would happen to that stack. So when we're done, make sure it's here, and if it's empty, it's empty. That's fine, it's going to be no big deal for us. We can handle that later. So this will add the last one. So when this is done, then I'll have my list of planes. So I should have that as self.trains, right? Self.planes. So I can keep these around later. Self.dot. I think I'm untabbed a little bit here. There we go. And then our train items. Oh goodness, gotta add self.dot everywhere here. Plain items, plain items, plain items. Okay. So we're done, we'll have 4 things. We'll have our list of trains, our list of planes, we'll have our train items queue of stacks, and our plain items queue. Okay, so that's the doc. So we should be able to load the doc, get it ready to go. That's one part of the problem. Right? The next part then is figuring out how long does it take. So we have to work all these items then. So maybe we have then a function for load, right? Load items. Right? We could do that. So load items, then we load the trains separately and we load the planes separately. So each one starts with a timer at 0. So maybe then we just say self.load trains and or we can make those separate. I don't know, self.load planes. Either way could work. Load trains. So we'll have a current time equals 0. right? That's our current time. Then we want to start loading things. So when we think about how we want to load things, right, we're using this transport method. Now, this could have a function for load, right? When we interact with it, we could add something to it. That's one option here. So we could have a function here for load item. To load the item, we need to know the current time, I guess. And then maybe we track then a number of items, start that off at 0. So every time we load an item, we'll take our self.number of items, and add 1 to it. And then we can say, hey, if my self.number of items is equal to the self.number of items needed, then my self.time until fully loaded is going to be the current time plus the one-way time. Self. All these are self-dots. Goodness. There we go. So if I've loaded all my items, done. Then what I can do is I can return the current time plus my self.one-way time times 2. Right, so I'm going to give back, hey, here's the time your worker gets back. The doc could track that, the transport method could track it. It's easy enough to track here because I know what the time is when I'm loading the item. Right, it's one way to go about it here. Now, you could definitely do this in the doc portion too. And either way could work for us. But if we think about the way we want to interact with classes, it's one option. So we can say, hey, here's the item to load. This way the transport method is tracking whether or not it's fully loaded or not. It has all the information it needs for that. So I kind of like that approach. Right? So then to load our trains, we'll say our current time is 0. And then now we need to make sure our queue has a length function as well. Right? We've got stack with length. Does our circular queue have a length? We have an is empty. Okay, so we'll check if we're not empty or not. Right? So while my self.train items queue of stacks.is empty, not. Right? Well, not is empty. Let's go do something here. Right? So we want to take the first stack off. So we'll say my current stack is my self.trade item queue of stacks.dq. Right? Grab the first item. I think that returns, right? DQ? Yeah, returns the item. Okay? And then while the current stack, or the length of the current stack does not equal 0, let's keep on going. So if it's empty, like if we just happen to add an empty stack this last time, we're just going to grab it, do nothing with it, and grab the next one. Right? The high-low driver gets confused when you tell him to take an empty stack off. It's like one of those moments you yell at the guy for not doing what he's supposed to do, and he's like, there's nothing to do. So if it's not empty, let's go work it. So we need to find the train number that this is going to. So that'll be the value on the top of the stack. So we'll grab the top item. So our train item then will be the current stack dot pop. Right? Pop the item off. That's where we're going to go. Then we need to find that train in our list of trains. Now, the way we built this here, I've got train number 1 at index 0, plane number 1 at index 0. That feels a little silly, right? So if we want, we could start with none here in the list so that everything gets shifted over one index. So plane number 1 is at index 1, train number 1 is at index 1. It's just fun that way, right? It makes life a little bit easier for us that way. And then really, we don't even need the transport index number. Right? We never even use that. We only use it for the factor of speed, right? Or how long it takes to get there, essentially. So to get there, then I'll take my self.trains at the train item number, and I'm going to say I want to load an item, and I have to give it the current time. And that's going to give me back a result. So I'll say my current time equals self.trains load item given the current time. This will automatically increment the time for me. Right? It's going to return the current time plus however long it took to get there and back, and then it will track when it's loaded or not all by itself. We already took care of that function here. So really, this is all we have to do to load our trains. Grab the front stack, grab the top item, load it. Keep on going, keep on going, keep on. Current time will keep incrementing itself as we go because load items does it. Again, you could have had all that logic in here. That's perfectly fine. Either approach would work. Right? And then loading planes is basically the same thing, but we don't even have to worry about the stack. Right? So for, I wanted the whole function here, sorry. Load planes. current time, and this is while our plain items for plain items queue, while it's not empty. This is the plain item. DQ the item, take our current time is, this will be planes at the plain item, load the item. Here's the current time. Unexpected types. DQ doesn't return anything? We did return, didn't we? DQ? It returns the item.
You still have the train variable there.
Oh, thank you. Okay, yep. So this is this will be load planes, plain item, train items queue. Yes, planes, thank you. Plain items queue.dq. Plain item. DQ doesn't return anything. Really? Why? Is it because we didn't define it to return something? Return the item. It should return something. I don't know, I think it'll work. We'll see. So after we load the items then, right, we wanted to print some output. We wanted to print the number of minutes it took to load each train. So I guess we could just say for train in self.trains, we want to print train dot time until fully loaded, and we want to change that ending character to a space, right, and do the same thing for our planes, and one more just print for a new line here between them here, right? So then for plane in planes, plain dot time until fully loaded, planes, there we go. So now we have to figure out how to get these values to the doc. That's the last piece here. So we have to make a doc then. So we could say doc equals a doc, and I can give it those values, right? Now, we didn't actually have to necessarily deal with input so much, right? There was no points for doing it. You probably did. Right? It's easiest to take these things as strings and then split them. Sure, so we could take a bunch of inputs. So we could say, I don't know, we'll make the doc and then we'll say line 1 equals an input, line 2 is an input, line 3 is an input. Yeah.
I'm sorry. Like on mine, I thought we could actually splitting the lines. Like I just call the doc class and give it like.
Yeah, if you passed it in what you wanted, that's great. This way we are going to handle the input. Just there's no points for doing it, but we probably should have because it mentions input and output, input from the keyboard. But I didn't give you any points for doing. Like we've done keyboard input. It's not interesting, so maybe we just skip it then, right? Because we say that's silly. We can do that. So we had the first list then was 271. The next one was 3 and 2. 3 and 2, and the next one was, I should just copy paste these, shouldn't I? That would be a little smarter. Another list. Oh, now I gotta add my commas though, shoot. Right, and then the last one, 2 1 1 2 1. That might just 2 1 1 1 1 2 1. Right, awesome. And then we'll call doc.load items. Load items. There we go. It probably has an S. Right, should we try it? See if it goes. Uh-oh. None type has no attribute. Time until fully loaded. Oh, because I added the first one. Shoot. Okay, so for trains, we have to slice then, right? From 1 to the end. Because I added in the dummy none at the start because I wanted to cheat. So we just 1 to the end. That'll probably work. Did it run? I hit run. Hey, let's see. 25, 36, 3. 25, 36, 3. 65 and 50. We should try another output though, right? Hopefully you tried more than one test because I don't know. Usually a good thing to do. Try some other inputs. Should we try some different values? Or just move these around a little bit, right? If we just move 3 to here and 1 to here, we'd expect this one to take an extra 2 minutes then, right? For train number 3, everything else would be the same. Maybe we move the planes then around too. So it took an extra 2 minutes, right? That's what we expected. Then we moved the planes around. Did this finish faster? Oh, because yeah, with the last round trip, we saved an extra 5 minutes. Okay. Yeah. So I think that about does it for the project. And this was just one way to go about it here. You didn't have to use a single transport item method or class. I think it's fun because they're basically the same thing, except for the one-way time is a little different. Yeah.
I think honestly the hardest part of the process is understanding the project.
Yeah. Figure out the input.
It's quite easy.
Yeah. Yeah, just a little bit of puzzling through what that input even means and drawing it out. You know, making sure we can, and then that is very similar to what we get in the real world. Like, write software, fix this problem, solve this problem. You really have to understand the problem you're solving before you can write software for it. It's really hard to write software if you don't know what you're actually supposed to be doing. So that's sort of like, let me get a lot of details out and figure it out and kind of work through it is very important, for sure, when we're designing solutions and things. Because sometimes we have something in our head and it's not what it actually should be. It's like talking through it with people is really helpful, for sure. So yeah, fun things. Go commit this to GitHub here.
And definitely the drawing that you made when you were explaining the project, that was really helpful.
Yeah, having a chance to draw it all out is good. So I don't want project 1, I want project 3. So like drawing things really is worth it. Like a picture is worth 1,000 words. I have a bunch of junk here that I made of projects I didn't want to keep, right? Yeah, I don't need that one. This one here. Okay. So here's project 3. With that, and I'm just going to discard all these. Oh, I think that's your project's graded. Project 1 at least is all in. I think the midterm's in as well. Should be there, and I got to go through and add your 2 and 3 now. Yeah, 2 and 3 that you added there. Okay. All right. So should we move on to some new stuff? We got a little bit of time here. Let's go back to.
So when are we getting our final product?
Today or Thursday. We can talk about it today, or we can talk about it Thursday. Either one. Okay. Let's wait till Thursday. Because that way we've got a little more time. We can focus on the new stuff, and then we'll leave. We finish up search trees, and we're not actually going to do too much with these because again, this is a topic you'll go into deeper next semester if you take 350. Yeah, so I think we can get through most of what we need to for search trees. Yeah. Okay. All right. So we'll talk about search trees. So let me pull up. We had done trees back when we did trees, and then prior to Q, used a tree structure, the binary tree structure. So with our search trees, we use binary search trees for those. So let me go start with a new project. This is week 12. Oh my goodness, week 12 already. 12 binary trees. Nope, hang on, it should have been binary search trees. That's okay. I can rename it. Factor, rename directory, binary search trees, and then I can rename it. I'm sorry?
Is it week 12?
Yeah.
I thought it was like 11. That's why.
It's been flying by. Well, so like I counted break as a week. So if you don't count break as a week, so it might be week 11. Other people count it that way. I don't know if that's more confusing or less confusing. All right, so our binary search trees. What did I do wrong here? I've got my Python interpreter. PyCharms is being weird. So I'm going to go back and grab our binary tree class. So we've got it here. We did our binary trees. Let's see. There's a regular tree, was a positional tree. Here's our binary tree. Positional linked binary tree. Sure, we can use that one. It's probably close for us. Now, we don't necessarily want to use the array-based storage for this one. And actually, we don't even really need the positions for this one either, because this will be a binary search tree. But we want to use nodes for sure. So let me take out positions, use binary tree node. This will be our binary search tree, binary tree node. So we don't need to validate positions because we're not going to use positions, we're not going to make positions. Don't even really use root either. Won't do left and right. Oh, taking out too many things then. So we're not going to add left, we're not going to add right. Not going to replace, delete. Okay. I'm just getting rid of everything, aren't I? That's obnoxious. All right, we'll just do it all with the node. That's fine. Probably get rid of everything else. All right, so we just have a node. Given some data? Sure, so we can start with some data. So what makes these special? Right? This whole idea, a binary search tree is a very specific form of a binary tree. In our binary tree, we had a node and it had 1 or 2 or 0 children. To be a binary search tree, we're going to be in a specific order. We're going to be in a sorted order. But the sort's going to be a little funny. So when we think about all of our nodes here, let me scroll down a little bit in here. No, I didn't want help. I just wanted to scroll down. There's a rule we have to follow. So again, this is a recursive structure where everything is a tree of the child class here. So the rule is that if a value is less than you have to be on the left. If a value is more than you, it has to be on the right. So of this tree rooted here, any value to the right of it has to be greater than it. Anywhere in the entire subtree. So of its children, and this is just all the descendants, all the way down. Right? You can't have something bigger or something less than anywhere else. This also means we're going to be a set, right? Because duplicates don't work very well with these sort of rules. Right? So we're going to be a unique set for this binary search tree here. So if it's a less than value, we have to be on the left. So this actually works relatively quickly here to start adding some values. So let's just put a couple in. So just shout a couple numbers at me, and we'll see how we can put them in based on these rules. So what number do we want to start with?
7.
7. Okay, so 7 goes here. We've got a 7. Now everything less than 7 will be on the left. Everything more than 7 will be on the right. So what's another number?
6.
6. All right, so we start at the root. We say, okay, are you not a duplicate? It's the first good check. Because if you are, we can't add, because we're a set. No good here. If you're not a duplicate, are you less than or greater than? So 6 less than or greater than 7. All right, so if we're less than, we have to go to the left. So if we're less than, we say, do you have a left child? No, there's no left child, so easy. You become the left child. 6, done. That was it. Let's try another number. 2, all right? Are you the same as 7? No, okay. So are you less than or greater than? And do you have a left child? So we're going to repeat the process with the tree rooted at 6. Just recursively call the same add function now with the tree rooted at 6. So are you 6? No? Okay. Are you less than or greater than? All right. Do you have a left child? Okay. So you become the left child. Done. We've added you in. If you have a left child, you just keep recursing. You just keep going down, 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 down these levels. So it's a recursive add, which is pretty easy, right? All we do is we check to make sure we're not a duplicate, and then if we're less than, we go to the left, greater than, we go to the right. If you don't have the child, you get added. If you do, you recurse with that child. All right, so let's try another number. 10. So are you 7? Is it greater than 7? Okay, so we go to the right. Do we have a right child? No? All right, we add a right child, we're done. Another number. All right, are you 7? No. Are you greater than 7 or less than 7? Right, do you already have a right child? All right, so recurse, so now 10. Are you 10? No duplicates. All right, are you less than or greater than? All right, left, do you have a left child? No, okay, so you get added as the left child, done. How about another number? 12, all right. Are you 7? No, greater than? Yeah, okay, recurse. We have a child. Are you greater than? Yeah. All right, do you have a right child? No, all right, add it in. We added a right child. What's another number? 5. All right, less than, equal to, or greater than? 1. All right, do you have a left child? Yes. All right, recurse. Less than, greater than, or equal to? 5. All right, do you have a left child? Yes. All right, recurse. Now we're on this one. Less than, greater than, equal to? Do you have a right child?
No.
All right, so now you're the right child. 5.
But what about the left one? I'm sorry, the right one to 6.
It just will never have a child, right? Because there is nothing between 6 and 7. Or, I mean, 6.5 if you want to do floating point numbers. So you don't have to have children here, because we're going to be in this binary search tree form where everything less than is on the left, everything greater than is on the right. So you can get into weird shapes. So that idea when we looked at the heap, we said, hey, we're going to be a full tree, every level will have filled, you don't have. Because we're not going to add things in the right numerical order to make sure every level's full. So it's not necessarily going to be efficient to store this in an array. Now, the things you'll get into later into like 350 is if you wanted to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to a binary search tree. The first thing is 1, and then 2, and then 3, and then 4, and then 5. You get the idea here. We're a list. We're a linked list. This is not very efficient here. So one of the things you'll get into is how do you rebalance the tree to be as close to full as possible? You don't have to be exactly full, where every level is completely full, but you want to be close to full. So really smart people who've done lots of math around this sort of thing determine something around like 3 generations of gaps is probably okay, something around there. I forget what the actual numbers are. But after that point, you want to rebalance so you have less height of the tree in relation to n items. Remember, the closer to full we are, the more guaranteed we are to have logarithmic performance. So, going down every level with the powers of 2, yeah.
So the problem with having a really deep tree is because when you recurse it, to traverse the whole tree, you need to go very deep in it.
So to add something new, like if I had 100 items, 1, 2, 3, 4, 5 in a row, to add 100, I'd have to check all 100 in that chain to find it. So it's going to be an O of n operation versus if I was in a pretty good form, like if I had 50 here in the middle and then like 25 over here and 75 over here, and like if it was perfectly split, you could fit 100 items in 7 levels or something like that. So you'd only have to do 7 checks of greater than, less than, or equal to. So it's a logarithmic performance at that point. So the closer we can get to that full structure where every level's full, the more items we can pack and have to do less checks as we kind of like plinko your way down, left, right, left, right, left, right, left, right, to find where you land. There's some cool like visualizations. So visualization, adding values to binary search tree. There's some good like University of San Francisco. Here we go. 10, 20, 30,
Interesting.
15, 25, 2. Like you can just like keep adding numbers here, right? But you get the idea.
It's actually beautiful to see.
Yeah. So this one lets me put in duplicates. This is a little confusing, but that's okay.
But why do you put it on the right instead of the left?
I don't usually allow duplicates because they confuse me. It messes with my rules. So I'm just gonna pretend we don't do duplicates. It makes my life easier. It's a more advanced thing. So we can just like keep adding things here, right? So as you go, you can get these really long chains or, I'm sorry?
I'm sorry, we've got like 3.
3, yep. So we'll go left and then right. 4, we'll go left, right, right. Right. So you get these interesting structures, right?
I really like it.
Yeah, this is kind of fun. So they've got some cool ones out there you can play with. There's one cool tool you can use that lets you kind of visualize this when you debug, but PyCharm doesn't have it, but that's okay. It's not the end of the world. Yeah.
Sir, why is it called a search tree? Like every search tree, right?
Yeah, so that's the piece here. So we did way back when we talked about a binary search. We said if you got a list of numbers and it's sorted, you start in the middle and then you split the difference, right? So that's essentially the binary search tree here, right? If we're in a good form here, the top node should be about the middle, right? And then you go less than to the left, greater than to the right. So each way, if we're in that full structure, you're cutting off half the tree as you go. Right? If you wanted to find, hey, do I have the number 13 in here? Okay, it's greater than, so I cut off the left half of the tree. It's greater than, I cut off another left half of the tree. So each time you're restricting your results. So they give you this form here.
It only works with numbers, right?
No, anything that's sortable, anything that has a less than and greater than. So that's why, like when we dealt with other objects, you have to add the less than function or the greater than function to compare them. You can store them. in a sorted order.
Like, what kind of data that you will use where these will actually come in?
Binary search trees or trees, and not necessarily, like, there's all sorts of interesting logic, essentially back databases. So any piece of data that's ever stored anywhere in the world essentially is stored somewhere in a fancy tree, because databases use them because they're fast. So they'll give really good performance. Heaps are cool, but you can't really store them and search them very well. So sorted order is very important for a lot of things. So the databases make a lot of use of sorted orders for things. Yeah. And then to get the data back out in the sorted order, we looked at a couple of those tree traversals. There's the in order, the post order, the pre-order, those sorts of things, like a depth first. I'm sorry? Oh yeah. But the in order traversal will now give me something in order in a binary search tree, right? Because in order traversal said left, yourself, and the right. So if you have a left node, go left and recurse. If you have a left node, go left and recurse. If you don't have a left node, you're done, so then you print yourself. So we get the 2, then we go to the right node. Do you have a left node? No. Do yourself 5. Do you have a right node? No. So we go back to the 6 here. We already did the left. We're going to do ourself as 6. There is no right. We go back to 7. We did all the left. We do 7. Now we go to the right. Go to the right and we recurse. Go to the left first. So we go down to 8. There is no left child, so we get 8. There is no right child. We come back to 10. We're doing the self. It's 10. We go to the right child. There's no left child, so we get 12. So the in order traversal, if you're in a binary search tree form, gives you items in order. That's why it's called in order. So if you keep them in a binary search tree form, you'll get them back out in that order, which is cool. And that works no matter what the structure of the tree looks like. Even if it was this ugly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 structure, left self or left center right will still give you the sorted order. Right? There's no left child, so I'm just getting center, 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 right? Center right, center right, center right. I'll get it in the sorted order. No matter what you do with this binary tree, that order will give you the stuff back out in order. So it's a cool way to store data, so we get very quick inserts. So when we start looking at how we can insert data, right, we'll get assuming we have somewhat of a full structure, we get O of log n performance. Right, because if we can keep mostly full, where every level is mostly full, we'll get close to that logarithmic performance like we did with heaps. Where heaps forced us to be in that structure, we're not forcing people. Eventually the fancy stuff will like rebalance trees and move things around and say, hey, your right side has too many nodes versus your left side, so you need to like shift a couple things over. That's a whole other process. We're just gonna forget about it here and not worry about it. There's a couple popular things you'll work through. It's like red-black trees and AVL trees are, I think, the common ones that smart people came up with. But generally we'll get logarithmic performance for inserts, right? And then to find a piece of information here. If we want to find some data here or to see if it contains, right, we can again get logarithmic performance. You say, hey, find the number 7. Right, it does a binary search for us, right? Start in the middle, cut off half the tree each time, cut off half, cut off half, cut off half, till you find it or you don't. So you get logarithmic performance for finding something. Same with like removing an item here. So removing some piece of data here. Again, we'll get logarithmic performance, which is really cool. There's a couple rules around removing things. Is you want to replace yourself with either the next smallest item is what we usually do. So if I wanted to replace 6 with the next smallest item, what you do is this recursive function. You're going to go to the left and then all the way right. Because to the left is smaller, and then all the way to the right will be the largest smaller item. Right? No matter how big that chain happens to be here. So as soon as you find a node, so if we had like a 4 over here, right, there is nothing smaller than 5. I'm sorry, there's nothing bigger than 5. Right? That's the next smallest item. This is the next largest. That's smaller than me. The terms here, I'm really confusing myself. I'm sorry. But if you want to remove 6, right, you have to find. You're going to put in its place the next item that is the biggest one that's less than 6. Right, so you go to the left and you go all the way right. As soon as you find one that doesn't have a right node, you know that's the biggest. So 5 must be the biggest. And if we don't have a right node, remember swaps are really easy when you only have one node or no nodes. It's super easy to swap a value. You just put 4 in its place. right? If 4 had children, sure, they just stay there. It's perfectly fine, right? But eventually you'll find a node that doesn't have a right child, so the swap is really easy to put 5 in its place here, doing it that way.
And what do you do with the 5?
So we're going to just put it in the place of 6. And then we take 5 out, and then whatever this now is now the right child, essentially. Whatever this had is the right child. Right? Using the positions is really easy. If we use the index-based storage, it gets to be a little tricky here with swapping things around. Right? But the linked storage here is super easy to swap. We don't have to shuffle anything else. Right? We just say, okay, here's your new child. Done.
What is the easiest way for you to keep adding like certain items in the tree? Like just keep the item and then go find its path automatically?
Yeah. So that's what we do. So to insert something, then we have to start at the root, and we're going to make sure is it less than, equal to, or greater than. Right? And then we'll recurse. So we'll have like probably a private helper function. We can define an insert here with the data and then the current node that we're looking at, right? So insert then would start with the node of root. So we're going to call self.insert given the data and then self.root, okay? And this one checks. Now, so if whatever node I'm starting with, right, because this is going to be recursive, I'm going to check if it equals, we'll raise an error. So if the node.data is equal to the data, we'll raise a value error or something. Can't have duplicates in this tree. Otherwise, then we'll check if we're less than. So if the node.data, if the data is less than the node.data, right, then we'll do that one, and then else we'll do the greater than. So if it's less than, we need to check if we have a left child. If node.leftChild is none, great, now we can add this as the left child. So we'll take my node.leftChild equals a new node, right? We'll add a new self.node, binary tree node, given the data. And then we have to tell it its parent then will be the node, right? And it doesn't have a left, it doesn't have a right. Those just stay nones here. Then we tell, right, our node, we know that's the left child, we're done. If it's not none, then, right, my else here is I'm going to recurse. I'll call self.insert, given the data, and my left child. Right? Just recurse on the left child. So just repeat the process, starting now with the tree rooted here. Right? Here's the new node to start checking. Are you equal to, less than, or greater than? So if we're greater than, we check, again, we're just going to repeat to see if we have a right child. Right child is none. Then the right child becomes a new node, with us being the parent. Otherwise, we're going to recurse on the right child. So this is insert. And it just keeps on recursing. So that's all we have to do, and it will sort itself left, right, left, right, left, right, till it finds an open spot. Right? If it's less than, it goes to the left until it is no longer another node there. Okay, now I can be your left child, or if I'm greater than, now I can be your right child. Or if we keep having children, we just keep going down, 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 down the levels. But because we're in a mostly full structure, we'll get logarithmic performance for adds, which is really nice. So if we think about adding stuff to a sorted list, right, you have to go find where it needs to go in the list, and then you have to insert and bump down n items. Right? Even if we could just do the binary search on a list, if I had 100 items on my list and said, hey, I want to add 27, or let me start in the middle because it's sorted, okay, it's 50, jump down to 25, and you eventually find the spot logarithmically. But to insert into a list, you have to bump n items down. So your insert performance on a sorted list is still O of n, because you have to do the shifting to make room. With our positions, with our nodes here, there's no shifting that has to happen. So we get to find where it goes logarithmically, and it just adds it in constant time. So it's always going to be logarithmic, assuming we keep this fullish balanced structure, right? That's sort of, again, we'll get to that later. We'll just hand wave and say we'll probably be like this for now. Right, so to insert, we just go ahead and do this recursive bit, starting at the root, and it inserts. Removing is a little trickier, right? So we need to find the data, then replace with the largest, smaller item. Right, and that was left child, and all the way right. And again, we'll get into all that code. We've got some time. We can get into it. Finding a particular value, right, is just doing the binary search, right? So we can say, okay, if we found the data at the node, great. And again, this was probably with like a helper to find given the data and the node, right? So we're going to return self.find given the data, and this is like, or I guess it should be contains, right? It's probably the better. Do we have a value, right? Is there value in this list, right? Finding it, we're not going to give them the position or anything. We don't do anything like that. So, okay, do we have the data here? So if the data is equal to the node.data, we're going to return true. If it's not, if we didn't return true, if the data is less than the node.data, let's check left. If the node.data, I'm sorry, node.left child is none, we're going to raise a value or return false, right? We don't have, if you don't have a left child and you're less than, you're not in the tree. Can't be here, right? Because if you were less than, you'd be to my left, right? There is nothing less than 2 in this tree. That's the farthest left item here, right? If I look at my tree here, there's nothing left of 2, so there's nothing less than 2. Otherwise, then, right, we'll return self.contains given the data and my node.left child. Right, just recurse starting my left child. Are you equal? True. If not, check. Right, and then so if we're not less than, right, and really those are both returns, so we don't need the else here. It's a little bit redundant. We can check if the node.right child is none, return false. Otherwise, return self.contains given the data and the node.right child. Right, that's sort of like an implied else here. We're going to return something otherwise. Right? So either return true, we found it, or we'll return a false, we don't have a left, or if you're greater, not less than, you must be greater than. Well, if you don't have a right, we'll return false. Or we just keep on recursing till we find it. So find is really quick, again, assuming we have a mostly full structure. They call this like a balanced structure, right? You have about the same number of items on the left end as on the right. If you imagine like the scales, right? If you're close to balanced, that's a quick way to look at it. You know, how many items do you have on the left versus how many items do you have on the right? A quick way to balance there. So removing will take a little bit more time. We should save that for Thursday. What do you think? Should we save it for Thursday? Otherwise, we're running out of stuff to do for Thursday. You want to do it now, or do you want to do it Thursday?
I have to go anyway.
That's right. Okay. Yeah. So we can save it for Thursday then. This was a lot already, so you can go ahead and commit this. So this is binary search tree started.
Thanks, Dave.
Yeah, no problem. See you Thursday. All right.
Sure.
Yeah.
Yeah, actually yesterday was really funny.